Here's Lesson 5, Applications of Quadratics. Earlier in this unit, you learned how to solve quadratic equations using the method of factoring, or the quadratic formula. In this lesson, we're going to learn why is it useful to be able to solve quadratic equations? What are the applications that have a quadratic relationship? And in this lesson, we're going to look specifically at projectile motion, maximizing profits, and different geometric relationships that are quadratic. So let's jump right into example 1. Example 1 says the equation h at t equals negative 4.9 t squared plus 60t plus 3 represents the path of a rocket where h is the height in meters and t is the time in seconds after it has been launched. Before I look at the 4 parts of this question, I'm just going to make a rough sketch of what I know this quadratic relationship is going to look like based on its standard form equation. So based on its standard form equation, I know since the a value, the leading coefficient, is negative, I know it's going to be opening down. And that makes sense based on this question because the rocket is going to be launched, meaning it's going to go up in the air, and then it's going to reach a max point and then come back down to the ground. I also know that the y-intercept is equal to the constant value, which in this case is 3. One other thing I want to point out is notice I was able to label my x-axis time because I see in the equation, in place of the independent variable x, I see t, which represents time in seconds. And I was able to label the y-axis height because in place of y, my dependent variable, I see h, height. Now let's answer the questions. Part A asks us, what is the height of the rocket when it is launched? Well, I actually already have that answer if I look at my diagram. When it is launched, that means when time is 0, because time is the time in seconds after it has been launched. So when time is 0, it hasn't been launched yet. So I need to evaluate the height when time is 0. And if we look at the equation, it's in function notation, which we haven't really seen before. It says h at t equals. Now that doesn't mean h multiplied by t. It's just a way of indicating that we're evaluating the height for whatever value of t we see in brackets beside the height. So if I want to evaluate the height when time is 0, I can just say h at 0 equals, and then substitute in 0 for time into my equation. And now that I've replaced the t's with a 0, when I evaluate this, all I'm left with is the constant value, 3. So the height, when time is 0, is equal to 3. Remember, h at 0 does not mean h multiplied by 0. It's just a way of indicating that the answer we have here, 3, is the height when time is 0. And I should include the units, 3 meters. Part B says how long does it take the rocket to land on the ground? If we look at the graph I've sketched, it's asking for us what is the time when h, the height, is 0. Well, I see the height would be 0 here at some time, and the height would also be 0 somewhere over here. Now, we don't actually care about this answer because it doesn't make sense in the context of our question, but when we solve algebraically using our quadratic equation, it will generate that answer that we'll have to reject. So if we're going to solve for when the height is 0 algebraically, I need to set the height to 0, so set h at t to 0, and then solve for the value of t that makes that true. Now to solve a quadratic equation, it has to be set to 0, which it already is, and now we have to choose between solving by factoring or solving using the quadratic formula. Based on the a value of negative 4.9, I don't think this quadratic is going to be solvable by factoring. So what I'm going to do instead is just go right to my quadratic formula that tells me I can solve for the independent variable, in this case t, by doing negative b, so negative 60, plus or minus the square root of b squared, so 60 squared, minus 4 times a, which is negative 4.9, times c, which is 3, all over 2 times a, so 2 times negative 4.9. And then when we're evaluating this, we should simplify under the square root first, and that gives me the square root of 3,658.8. And now I can split this into my 2 possible answers. My first answer I can generate by doing negative 60 plus that square root, all divided by negative 9.8. And that gives me approximately negative 0.05 seconds. And my second answer I can get by doing negative 60 minus that square root, all divided by negative 9.8. And I get approximately 12.29 seconds. So if we look over at the diagram, I now know the times when the height is 0. The times are negative 0.05 seconds and 12.29 seconds. Now, in the context of this question, it says t is the time in seconds after it has been launched. So it only makes sense for us to be considering time values that are greater than or equal to 0. That would be the domain of this function. So we can ignore any negative time answers in these questions. So I will reject that first answer, and I know that to answer part B, when does the object land on the ground? It lands on the ground after 12.29 seconds. Let's now look at part C. Part C says, what is the maximum height of the rocket? Any question about a max or a min is asking about the vertex, but what specifically about the vertex does it want to know? Remember, any point has an x and a y coordinate, and in this question, x is time and y is height. So every point has a time as the x coordinate and a height as the y coordinate. The question wants to know what's the max height, so it's interested in what is the y coordinate of this vertex. There are many ways we can find the y coordinate of a vertex. We could convert the standard form equation into vertex form by completing the square, but I think it would be more efficient if instead, if we solve for the x coordinate of the vertex, which in this question is time, by using the formula negative b over 2a, substituting that answer into the original equation for our time, and solving for height. So the x coordinate of the vertex, which in this question is time, the formula is negative b over 2a. If I look at the original equation, that would tell me to do negative 60 over 2 times negative 4.9. And if I evaluate that, I get 6.12. So in my diagram, I know the x coordinate of the vertex is 6.12. It reaches a maximum height at 6.12 seconds. But what is the maximum height? What's the height when time is 6.12? We can get that height, the y coordinate of the vertex, by substituting in 6.12 for time and solving for the height. And when I do that, I get 186.7 meters. So I now know the y coordinate of the vertex is 186.7. So max height, my answer to C, is 186.7 meters. The last part of this question, part D, says when is the rocket 4 meters above the ground? If we look at the diagram, the height of the rocket starts off at 3 meters above the ground, and then goes up to the max height, and then down back to the ground. So it's going to be at a height of 4 meters pretty soon after it's launched, and then again on its way back down. So there are two places where the height is 4. So the y-coordinate, the heights of both of these points is 4. But what are the times that the height is at 4? So I'm interested in what are the x-coordinates, the times, of those 2 points that I just drew on the graph. If I'm going to figure out the time when the height is 4, in my equation, I need to set the height equal to 4, and then solve for t. And then if we're going to solve a quadratic equation, it needs to be set to 0. So I need to take the 4 and move it to the other side. When I subtract the 4 to the other side, I'll be able to collect it with my constant value of 3. And 3 minus 4 is negative 1. And then to solve this quadratic, once again, we could try and factor it, but it's not going to be factorable, so we'll use quadratic formula. If I plug into quadratic formula, it would be negative 60 plus or minus the square root of 60 squared minus 4 times negative 4.9 times negative 1 all over 2 times negative 4.9. Now because I'm running out of room, I'm just going to evaluate this all in one step. I will get 2 answers for t. We can get the first answer by doing negative 60 plus that whole square root, all divided by negative 9.8. And I can get my second answer by doing negative 60 minus that whole square root, divided by negative 9.8. And my 2 answers for time are approximately 0.02 and 12.23 seconds. So if we look back to the diagram, I now know the x-coordinates of those 2 points that have a height of 4. The x-coordinates are 0.02 and 12.23. Alright, that's example 1 done. I think that's the example that will take us the longest amount of time. We've got a few more examples to do. Let's move on to example 2. Example 2 says one leg of a right triangle is 1 centimeter longer than the other leg. The length of the hypotenuse is 9 centimeters greater than that of the shorter leg. Find the length of the three sides. So like I said, for these problems, it's often helpful to draw yourself a diagram. So I've drawn a right triangle. It doesn't have to be to scale. It just has to be accurate enough that you can label what the question tells you and then figure out how you can make an equation to solve for your unknowns. It says one leg of the right triangle is 1 centimeter longer than the other leg. So the legs are the shorter two sides. I'll call one of them x, and it says the other one is 1 centimeter longer than that. So I'll call that x plus 1. It then tells me the length of the hypotenuse, which is of course the side across from the right angle, is 9 centimeters greater than that of the shorter leg. So the shorter leg is x, the hypotenuse is 9 bigger than that, so I'll call that x plus 9. And then the question asks us to find the length of all three sides. If I'm going to be able to solve for x, you need to remember the relationship between the three sides in any right triangle. Pythagorean theorem tells us that the sum of the squares of the shorter two legs is equal to the square of the longest side, the hypotenuse. If I set up my equation, I could say that x squared plus x plus 1 squared is equal to x plus 9 squared. And then from here, it's just a matter of solving for x. I notice that it's going to be a quadratic equation, so I'm going to have to expand all of this, collect all my like terms, set it to 0, and then solve. To expand it, you're going to have to remember that to do x plus 1 squared, that means x plus 1 times another factor of x plus 1. So I'll rewrite it like that. And x plus 9 squared means we have two factors of x plus 9 being multiplied together. And then when I do those multiplications, you'll have to remember to follow the method of FOIL, which tells you you're going to have to multiply each term in the first binomial by each term in the second binomial. And when I find all of those products, I would have x squared plus x plus another x plus 1 equals x squared plus 9x plus another 9x plus 81. We'll now collect all our like terms. On the left side of the equation, I have 2x squareds, and I have 2 x's, and a positive 1. On the right side, I have an x squared plus 18x plus 81. Now, if we're going to want to solve this equation, we have to set it to 0, so we'll move all the terms to one side. I'll move them all to the left, and while I'm moving the terms from the right to the left, I'm going to write them beside their like terms. So I'll subtract the x squared to the left side of the equation. I'll subtract the 18x, and then I'll subtract the 81. On the right side of the equation, we're left with 0. If I collect everything on the left, I have x squared minus 16x minus 80 equals 0. I now have my quadratic set to 0. I now need to solve this. We could use quadratic formula, but notice this is a quadratic where the a value is 1. We could factor it by finding numbers that multiply to the c value, negative 80, and add to the b value, negative 16. The numbers that satisfy that product and sum are negative 20 and 4. So this would factor to x minus 20 times x plus 4. And once we have a product of factors equals to 0, we can use the zero product rule that tells me if that equation is going to be equal to 0, one of the factors has to be equal to 0. So set each factor to 0 and solve for which value of x makes either of those factors be 0. The first factor would be 0 if x was 20. The second factor would be 0 if x was negative 4. And then we'll look at those answers and see how they relate to our question and see if they're both acceptable answers. The question wants us to find the length of all three sides. If x is negative 4, that would mean the first side is negative 4 centimeters. That doesn't make any sense in the context of this question. We can't have a negative length. But x could be 20. That would make the shorter leg equal to 20. It would make the longer leg equal to 21. And it would make the hypotenuse equal to 29. And I should write the units with all of these. These are all in centimeters. So there's my final answer. There are the lengths of all three sides. Example 3 is another geometric relationship that's quadratic. It says the length of a rectangle is 16 centimeters greater than its width. The area is 35 centimeters squared. Find the dimensions of the rectangle. And then we need to come up with an equation showing the relationship between the dimensions and the area so that I can solve for my value of x. And for a rectangle, we know that area equals length times width. So in this question, it would be 35 equals x times x plus 16. And notice I wrote the factor of the width before the factor of the length, but the order of multiplication doesn't matter, so that's fine. I just wrote it that way because when we do our expanding, it'll be easier to think of it in that order. In order to solve this equation, we are going to have to expand it, so I'll have to distribute my x to both terms in the binomial. And when I do that multiplying, x times x is x squared, and 16 times x is 16x. I see that it's a quadratic equation because it has an x squared. Set it to 0 by moving the 35 to the other side. And then we're going to need to solve this quadratic. It has an a value of 1, so it might be useful to see if it's factorable. Do any numbers multiply to negative 35 and add to 16? There is no pair of integers that satisfy that product in sum. But if you weren't sure, you could check the discriminant, b squared minus 4ac, and see if it's a perfect square number. 16 squared minus 4 times 1 times negative 35 is 396, and 396, notice it's not a perfect square number. When I square root it, I get an irrational number. So that tells me this quadratic is not factorable. But because the discriminant was positive, I do know there are going to be two solutions to this quadratic. They're just going to be irrational solutions, but we do need to find them. So to find those irrational solutions, we'll have to use quadratic formula, which tells me to do x equals negative b, so negative 16, plus or minus the square root of b squared minus 4ac, 16 squared, minus 4 times 1 times negative 35. And all of this needs to be divided by 2a, so 2 times 1. I already evaluated the discriminant. It was equal to 396. So I can split this into my two possible answers by doing negative 16 plus the square root of 396 all over 2, and doing negative 16 minus the square root of 396 all over 2. And my two possible answers are negative 17.95 and 1.95. Because this question is about side lengths, I know that I can't have a negative answer, so I can reject the negative 17.95 and just use 1.95 to calculate my final answer. My final answer, the question wants to know what are the dimensions, so I'll need to write what the width and the length are equal to. The width is equal to x, which is 1.95 centimeters, and the length is equal to x plus 16, so it would be 17.95 centimeters. And these are approximate answers. We had to round because we got irrational solutions for the solutions to our quadratic equation. But if we check based on those dimensions what the area is, by doing length times width, it should be approximately 35. Two more examples to do. Example 4, path of the soccer ball after it is kicked from a height of 0.5 meters above the ground is given by the following equation, where in that equation, h is the height in meters and d is the horizontal distance from the person kicking it in meters. Once again, before I even analyze what it's asking me to find, I'm going to make a rough sketch of the relationship. I know from the quadratic, since the a value, the leading coefficient, is negative, the quadratic is going to be opening down. After it's kicked, the ball must go up and then come back down. And I can see from the constant value, the c value, 0.5, the y-intercept is 0.5. And the question even tells me that's the height that it's kicked from. And notice I was able to label the y-axis my height and my x-axis the horizontal distance. Part A asks us how far has the soccer ball traveled horizontally when it lands on the ground. Well, when it lands on the ground, its height is going to be 0. So its height is 0 at this point. And we want to know what is the horizontal distance. So what is the x value, or in this case the d value, that has that height of 0. So this point is what, comma 0. If we're going to solve for the d value that makes h 0, in the equation, we'll have to set the height to 0 and solve for d. And you'll notice I already have a quadratic equation set to 0. So to solve this, we're either going to try and solve it by factoring or using the quadratic formula. I might want to try and solve this one by factoring. Before I try and find any product and sum information, let's see if we can common factor out that a value of negative 0.1. If I take that out as my first factor and then divide all of the terms by negative 0.1, I would be left with d squared minus 10d minus 5. And then this product would be 0 if either factor was 0. And I know negative 0.1 can't be 0. But the second factor, the d squared minus 10d minus 5, maybe there are values of d that would make that be 0. So we'll focus on how could that factor be 0. Another way to think of it, you could think of that negative 0.1, that constant factor, being divided to the other side, and 0 divided by negative 0.1 is 0, so it's gone. If I tried to solve this quadratic by factoring, there are no numbers that multiply to negative 5 and add to negative 10, so we'll have to use quadratic formula, which tells us the independent variable, d, is equal to negative b, so 10, plus or minus the square root of b squared, so negative 10 squared, minus 4 times a times c, all over 2 times the a value. And then because I'm running out of room, I'll evaluate all of this at one time. Underneath the square root, the discriminant is 120. So as I evaluate this, I'll just type 120 underneath the square root. So my first possible answer will be 10 plus root 120 over 2. And my second possible answer will be 10 minus the square root of 120 over 2. And my possible answers are negative 0.48 and 10.48. In this case, our units are meters. It's the horizontal distance that the ball has traveled from the person that kicked it. So once again, in this question, our equation generated an answer, a negative answer, that doesn't make sense in the context of this question. So we can reject our negative 0.48 answer and use our answer of 10.48 as the answer to part A. Part B says find the horizontal distance when the soccer ball is at a height of 2.6 meters above the ground. When the ball is kicked, it's at a height of 0.5. It then goes up to some max height, which we'll solve in part C, and then comes back down to the ground. This question wants to know when is it 2.6 meters above the ground. I'm just going to pick two places where I'm guessing the height might be 2.6. And the question wants to know what are the x-coordinates of those 2 points that have a height of 2.6. What are the horizontal distances that the ball has traveled when it gets to that height of 2.6? It's going to pass the height of 2.6 on the way up, and then also again on the way down. Let's solve for those two values. If we're going to solve for the horizontal distance when height is 2.6, we will set the height equation to 2.6. 2.6 equals negative 0.1 d squared plus d plus 0.5. And then we'll need to solve this quadratic equation. Step 1 is always setting it to 0. Move the 2.6 to the other side. 0.5 minus 2.6 is negative 2.1. Then once again, I'm going to try and see if this is solvable by factoring. I'll common factor out the negative 0.1 first. That leaves me with d squared minus 10d plus 21. And then I notice inside the brackets, the quadratic is factorable. Since the leading coefficient of the quadratic in brackets is 1, I can find numbers who have a product of 21 and a sum of negative 10. The numbers that satisfy that product and sum are negative 7 and negative 3. That quadratic in brackets can factor to d minus 7 times d minus 3. If we want to know how a product of factors can be 0, we just look at how could each factor be 0. The constant factor can't be 0, but d minus 7 could be 0 if d was 7, and d minus 3 could be 0 if d was 3. So I have two horizontal distances where the height is 2.6, at 7 meters from the person that kicked the ball and at 3 meters from the person that kicked the ball. If I look over at my diagram, I now know the x-coordinates of those points. At 3 meters and at 7 meters, the height is 2.6. Part C wants to know what is the max height of the ball. If you see the word max, we know that it's asking something about the vertex. If we want to know the max height, well, height is the y-coordinate of the vertex, so we're interested in what is the y-coordinate of the vertex. This vertex has an x and y coordinate. The x-coordinate is the horizontal distance, which the equation calls d. The y-coordinate is the height, which the equation calls h. We're interested in the y-coordinate of the vertex. There are lots of ways we could find this, but if we look at all the points we have on the quadratic, and if you remember that quadratics are symmetrical, we could find the x-coordinate of the vertex, the horizontal distance, just by finding the average of any pair of points that have the same height. So I could find the average between 3 and 7, or I could find the average between negative 4.8 and 10.48. Either way, we would then find the x-coordinate of the middle of the parabola, which we know is where the vertex is. So for part C, how would I average 3 and 7? The x-coordinate of the vertex, which is our horizontal distance, I could just average 3 and 7 by adding them, dividing by 2, and I get 5. So I know the x-coordinate of my vertex is 5. It reaches its max height when the horizontal distance from the person that kicks it is 5 meters. But what is the max height? What's the y-coordinate of the vertex? We can calculate that by taking our answer of 5 and substituting it into our equation. If I substitute it in for d, I get an answer of 3. And these answers are both in meters. So over at my diagram, I now know that the height is 3. So the max height of the soccer ball is 3 meters. Let's now move on to our very last question. In this question, we're going to be looking at how to maximize revenue. A sporting goods store sells 90 ski jackets in a season for $200 each. Each $10 decrease in price would result in 5 more jackets being sold. And that should make sense. If you decrease the price of something, you're going to sell more of the items. At what price should they sell the jackets in order to obtain a maximum revenue? And what is the maximum revenue? First thing that should stand out to you is the word maximum. And what we know about quadratics is that they all have a vertex, which we consider a max or a min value. So this question is going to have to do with finding the maximum, so the vertex of a quadratic. There's going to be a couple things for this question you're going to have to understand before we can start to do it. First of all, you have to know what revenue is. That's like the income that the company is going to be generating. And a general formula for revenue is that revenue can always be calculated by doing the number of objects that you sell multiplied by the price that you sell those objects for. So if we think about the revenue the company had when they sold 90 jackets for $200, that would be $18,000. What the company is thinking of doing, they're thinking about decreasing the price by $10 a certain number of times to try and obtain a higher revenue. Now, they don't want to decrease the price by $10 20 times, because that would bring the price of the jackets to $0. And then, of course, their revenue is going to be nothing. But maybe there is a certain number of decreases in price that although they're going to be making less per jacket, they're going to be selling so many more that it's going to increase their revenue to a maximum revenue. Let me draw a diagram of this relationship. So if you look at my graph, let's look at a couple things. First of all, the y-axis I've labeled revenue. That's going to be my dependent variable. And what does that depend on? In this question, it depends on how many times they're going to decrease the price by $10. So actually, let me, at the start of my question, let me define n, I'll make that my independent variable, as number of $10 price decreases. And then you can see, based on how I drew the relationship, I'm assuming that as they decrease the price by $10 a certain number of times, the revenue is going to go up. They're going to start to sell more jackets, but the jackets are going to be sold for less. But I'm assuming that the revenue is going to start to go up. And then after a certain number of price decreases, they're going to be selling the jackets for so little amount of money, it doesn't matter how many they're going to be selling, the revenue is going to start to go down. What the question wants us to know, at what price should they sell the jackets for in order to obtain a maximum revenue? And what is the maximum revenue? So the question is going to be asking us for information about this vertex right here. If we figure out the x-coordinate of that vertex, or in this case, n, number of $10 price decreases, and the y-coordinate of this vertex, in this case, the revenue. So now let's go over to the equation I created for revenue and try and write the revenue in terms of the number of $10 price decreases. If we analyze numbers sold, we know that originally they sold 90 ski jackets, but that number is going to go up by 5 every time they decrease the price by $10. So it's going to go up by 5 n times. And the price, it started out at $200, but they're thinking about decreasing that price by $10 a certain number of times. So decreasing it by 10 n times. Here's my equation for revenue. We want to use that equation for revenue to determine the coordinates of the vertex, and then I'll use those coordinates to answer the question. If I want the vertex of a quadratic, I could either convert this to standard form, and then from standard form either complete the square, or use negative b over 2a to help find the information about the vertex. Or because it's already in factored form, I could use the factored form to find the x-intercepts, which would be the places where the revenue is 0, which would be here and here. And then I know parabolas are symmetrical, so I can average those values to find the x-coordinate of the vertex. Since it's already in factored form, I think that's what I'll do. I'll set the revenue to 0 and then solve for the values of n, which get me those x-intercepts. A product is 0 if either factor is 0, so let me set both factors to 0, and then I'll solve both of those equations. The first equation, I'll subtract the 90 to the other side, and then divide the 5 to get me negative 18. So this diagram is definitely not to scale, so I know this n value, negative 18, is a place where the revenue is 0. In this case, a negative n value, decreasing the price negative 18 times, I guess that would mean increasing the price by $10 18 times. So they could increase the price by $10 18 times, and that would end up making them sell 0 jackets, so the revenue would be 0. Or if I solve the second equation, I'll add the 10n to the other side, and then divide the 10, and I get n equals 20. So I now know the x-coordinate of this point is 20. So if they decrease the price by $10 20 times, that would make the price go to 0. So it doesn't matter how many they sell. If they're selling them for $0, of course the revenue is going to be 0. And now I'll use the fact that parabolas are symmetrical to find the x-coordinate of the vertex. I can add my x-intercepts, negative 18 and 20, and then divide that by 2 to find the average of them, and that gives me 1. So the x-coordinate of the vertex, which stands for the number of $10 price decreases, is 1. So one $10 decrease. That's going to get us to the vertex, which is going to be the max revenue. And what is that max revenue? Let's find the y-coordinate of the vertex, which we would get by taking the value of 1 for n and subbing it into our revenue equation. If I sub it into the revenue equation for n, 90 plus 5 times 1, multiplied by 200 minus 10 times 1. And before I evaluate this, remember what these factors stand for in this question. The first factor is number sold, and the second factor is price. If I simplify the factor for number sold, 90 plus 5 is 95. That means they would sell 95 jackets. And each jacket, how much would it cost? If I decrease the price by $10 once, it brings the price to $190. So if the jackets cost $190, 95 people will buy them. And that's going to generate a maximum revenue of $18,050. So in the diagram, I now know the y-coordinate of the vertex is 18,050. So with all this information, I should be able to answer the original question. What does it ask? It says, what price should they sell the jackets in order to obtain a max revenue, and what is the max revenue? If we look at my calculations, the price that generates the max revenue is $190, and the max revenue is $18,050. Selling the jackets for $190 generates a max revenue of $18,050. That's the end of that lesson. Hopefully you now understand some applications of quadratics, and you feel comfortable setting up the equations and solving for what the question is asking for.